Hey guys, this is notes number 7. I think it's 7. Don't trust me on my numbers, okay? Here's your FLT. Write it down, and we'll get started. Given a Taylor or Maclaurin series, okay, you're going to be able to find what we call the radius of convergence. It's not that bad at all. So in the last few lessons, the last 3 or 4 lessons, you guys were learning all the different ways that you can test for convergence. Okay? Test to see where they can overlap and share the same values. Okay? So the thing is, with a power series, you're testing it at specific values. Okay? So how can we generalize it so that we can think of all the x values that can make it converge? Okay? So now we're going from a numerical to an analytical point here, okay? We're trying to find out, well, what are all the x values I could use so that the series will converge, all right? And this is called the radius of convergence. So here we go. So remember when you guys had a graph, okay? You're trying to see where they overlap. And where they overlap is going to be your radius of convergence. So there's always a center. And in this case, the center is not always going to be 0, but I'm going to use it as our example. So suppose we had a center at x equals 0. Okay? How far out you go from 0 to where it overlaps is going to be your radius of convergence. So this right here is kind of like your interval, which we'll talk about. How far out can I go from my center to the point where the two functions are going to overlap and share the same values? Okay? So remember, it's not so important to find out where a series diverges. It's more important to see where it converges, because that's when we could actually use the polynomial lookalikes, okay? So here we go. Find the radius of convergence. Here's what you guys do. Remember that last test that we ran, okay? We used the ratio test. It's important because that specific test we carry on over to finding the radius and later the interval of convergence, okay? So here's what you do. We're going to take the limit. We're going to run that ratio test as n goes to infinity. So remember, number one mistake people make, they forget the absolute value bars, okay? We're going to replace every n for n plus 1. So this is going to be 3 times x minus 2 to the n plus 1 all over the same thing. Okay? This one is a lot easier to reduce out. I noticed that the 3's reduce out here. If you see it already, you could probably make the adjustments there, but in the numerator, x minus 2 to the n plus 1 is the same thing as x minus 2 to the n times x minus 2 to the first power. And I write it like that so that I could actually reduce out the x minus 2 to the n's. So we're going to be left with the limit as n goes to infinity of the absolute value of x minus 2. Okay? So this is a little bit backwards in that we're going to force this ratio test to pass. So if you look back at your test, we're going to purposely make it converge. Okay? So if we want it to converge here, we're going to force that limit to come out to less than 1. Okay? So here we go. So you will do this every single time. You will set it less than 1. Okay? Make a note of that in your notes. Okay? Now, when n goes to infinity, I still get the absolute value of x minus 2. If you notice, there are no more n's in this problem. So when I take the limit, I actually get the same thing. I just get the absolute value of x minus 2 is less than 1. Okay, so a little bit of an algebra review here. When you have an absolute value that's less than inequality, what you could do is you create a compound inequality. So basically what that means is you go from here to here. You create a compound where the right side is positive 1 and the left side is negative 1. Without the absolute value bars, you cannot do that. And that's what a lot of people forget to do. They forget to put the absolute value bars. They go through everything here and they forget that last piece. Okay? This right here is basically your interval of convergence. We'll talk about that in a second, okay? So if I were to get x by itself here, I would have to move the negative 2. And how would I do that? I would add 2 here, add 2 here, add 2 here. Okay? Now that x is by itself, I get 3 and 1. Okay? There's actually 2 ways that you guys can do this. Okay? So I'm going from 1 all the way to 3. That is my distance, okay? So let's think about this logically and I'll show you all the shortcuts. So this right here is my diameter. Okay? What's the distance from 1 to 3? That's a distance of 2. So what is my radius? Okay? Well, if the diameter is 2, the radius is half, that's going to be 1. So basically what you're doing here is you're doing 3 minus 1 divided by 2 to get your radius. Happens to come out to 1. Okay? The easier way is if you take a look at this. Once you get the absolute value by itself, whatever number is over here is your radius. Okay? This actually represents your center. So the center, take a look, the center is at 2 and you're traveling 1 unit to the right and 1 unit to the left, which is exactly what I drew over here. Okay? So whichever way you guys are comfortable with, all right? We just want to find the radius. So the radius of convergence is 1. All right? Cool. Now the intervals we'll talk about in the next lesson, okay? All right, here's part, I guess that was example 1, part A. Let's call this part B. Okay, here we go. We're going to run the ratio test. We're going to force it to converge, okay? So we take the limit as n goes to infinity of the absolute value of n plus 1, x to the n plus 1, all over 10 to the n plus 1. And we're going to divide it by the a sub n term, or the same thing as multiplying by its reciprocal. Okay? By now, you guys should be able to understand this step here, okay? X to the n plus 1 and x to the n, that's going to reduce out to x to the first. If you don't get that, I encourage you to break it down, okay? Same thing here, 10 to the n and 10 to the n plus 1 will reduce out to 10 to the first down below. The n plus 1 and the n can't cancel out because they're not factors. So here's what we have. The limit as n goes to infinity of the absolute value of n plus 1 times x all over 10 to the first times n. Okay, so look, we want this to converge, so we force it to be less than 1. This one is slightly different because you actually have n terms here. So we're only paying attention to the n values, okay? When n goes to infinity, you're only staring at this. Where is it getting larger faster? They're actually traveling at the same speed. So that essentially goes away out to 1, and you're just going to be left with the absolute value. You know what? Let me write this out so it makes a little bit more sense. the x and the 10 have nothing to do with the limit. So we could actually take out the absolute value of x over 10 times the limit as n goes to infinity of n plus 1 over n. Okay? I'll write it out step by step for you guys. That limit comes out to 1. And I'll bring out my absolute value here. Okay? So what I have left here is I have the absolute value of x over 10 is less than 1. Okay? So that's the same thing as the absolute value of x over 10 is less than 1. All right? That 10 you could actually move over by multiplying by 10, and you would get this. Now that I have a simple linear on the left, that tells me that my radius is 10. And that's it. Okay? It's centered at 0. Okay, so basically what's happening here, you guys, is I have a x value of 0, and I'm going to go out 10 units to the right and 10 units to the left. So pretty much if I use any x value in between negative 10 and 10, this series will always converge. And that's the general idea of it, okay? So you guys are learning how to find the radius of convergence, but what does it really mean? What it means is if you choose any value within negative 10 and 10, and you plug it into the x value here, that series will always converge, all right? So this is different in that we're trying to find out all the values that work, whereas in the last few lessons, you were only looking at specific values to see if they work, all right? So it kind of speeds up the process. Let's do a couple more. Here we go. Part C. Try it out and then press play whenever you're ready, okay? All right, here we take the limit as n goes to infinity. Absolute value, negative 1 to the n plus 1, x to the 2 times n plus 1 plus 1, all over 2 times n plus 1 quantity factorial. I might need more space. Times the reciprocal, which is 2n plus 1 factorial, all over negative 1 to the n, x to the 2n plus 1. Now, first thing, make sure you use parentheses. Because if you replace an n with an n plus 1, that 2 is going to distribute, okay? Here we go. So I know that since there's an absolute value here, my alternating factors can just go away because they're going to turn out positive anyways, all right? This down here becomes 2n plus 3 factorial, because if you distribute the 2, you get 2n plus 2 plus another one is 2n plus 3. And up here is 2n plus 1 factorial. Well, I'm trying to cross some things out. Okay, so keep that in mind. Up top here, I also get x to the 2n plus 3, whereas the bottom I have x to the 2n plus 1. So what we can do here is 2n plus 3 factorial is the same thing as 2n plus 3 times 2n plus 1 less, 2, times 2n plus 1 less, 1. And I'm going to stop there because I noticed that I have a common factorial in the numerator. Okay? Okay, so even more so, x to the 2n plus 3, I could view that as x to the 2n times x cubed. And down below, that's just x to the 2n times x to the first. Okay? Again, you got to be really organized so you can see what you have left here. So I noticed that 2n plus 1 factorials are going to go away. X to the 2n is going to go away. And one of my x's is going to go away, giving me 2 left at the top. All right, here we go. The limit as n goes to infinity, I have x squared all over 2n plus 3, 2n plus 2. I think I got everything there. Okay, and I'm going to force it to converge. So I make it less than 1. N is going to infinity, so x squared has nothing to do with it. I'm going to pop that outside. Now I just have the limit as n goes to infinity of 1 over 2n plus 3, 2n plus 2. It's obviously getting larger in the denominator, so you know that limit there is going to come out to 0. So take a look now. What I have left is x squared times 0 is less than 1. But the thing is, when you multiply something by 0, you will get 0. Right? So what does that mean? Your radius is infinity. It's all real numbers. Okay, you could also write all real numbers if you wanted to. Because if x was -5 or -10 or positive 42, that limit will still come out less than 1, implying that the series will converge by the ratio test. Okay, so this is one of those rare cases where the limit comes out to 0 and then you're using the entire number line there. Okay, all right, here's another one. Try it out. Part D, I think. Is it D? Yeah, part D. Try it out. Press play when you're ready. Okay, here, limit as n goes to infinity, absolute value of n plus 1 quantity factorial, x to the n plus 1, all over n factorial, x to the n. If you do this long enough, you could tell that if you reduce those, you're going to have an n plus 1 left over. If you reduce these, you're going to have x to the first left over. If you're not comfortable with that, don't do that, okay? We're going to force this to converge. N is going to infinity, so the x factor there has nothing to do with it, so we can pull it out. The limit as n goes to infinity, I should put the absolute value bars, of n plus 1 is less than 1. So this is where it gets a little weird. The limit as n plus 1 of n plus 1 as n goes to infinity actually comes out to infinity. So is there any x value here that'll make this true? Okay, so this is one of those rare cases where this is only going to work if x equals 0, because if you have x as 0, that'll definitely be less than 1, but your radius is basically 0. Okay, because there's only one number that'll actually work. Okay, again, don't put too much emphasis on this. This is what you would call a rare case, okay? Okay, that's it. Radius of convergence. You're trying to find out how far from the center, okay? What values can I use to make this converge? All right? Practice it. It's not that bad. When we get into the interval of convergence, you guys are going to see how it's used even more. Thanks.